We continue investigating Chapter 2, which is about relational thinking. In this unit, we discuss functions. We'll see the definition of a function and several examples. We'll then investigate one-to-one and onto functions. And finally, we will learn how to produce new functions from old, chiefly by function composition. A function from a set x to a set y is a rule that assigns to each element of x a single element of y. And if f denotes such a rule, we write this notation to indicate the function. Now further, if we have an element x in x, we let f of x denote the element of y that's assigned to x. So we can think about these elements little x in the set capital X as being inputs, and the f of x objects over in capital Y as being outputs. So the set x of inputs is called the domain of the function, while the set y of potential outputs is called the codomain. Here we have an example of a function. In this instance, the set x, the domain, or the collection of inputs, is the set 1, 2, 3, and the set y, the codomain, which is the set of possible outputs, is 1, 2, 3, 4. Now we need a rule that assigns each element of x a single element of y, and that rule is given in this case by a formula, f of x equals x plus 1. But even if you didn't know that formula, you could look down at the picture and see how elements of x are being assigned to elements of y. So let's make sure that this really does satisfy the definition of a function that was given on the previous slide. So the first thing is that we need to have happen is that every element of x needs to be used. And indeed, we look throughout x and every single element, 1, 2, 3, they are all used. The next thing we need to do is to check that every element of x is assigned to a single element of y. So we look there and look at the number 1. That input is assigned to a single output, namely 2. The number or input 2 is assigned to a single output, namely 3. And 3 is assigned to a single output, namely 4. Now, let's suppose how can we screw this up, right? Well, one thing I could do, suppose this diagram also included this arrow. If the diagram included that arrow, then this relationship would no longer be a function because the element 1 in x would not be assigned to a single element of y. It's assigned to 2 elements of y. So we don't want an arrow like that to be included. Now, one thing you might be concerned about, and it's a reasonable concern, is that over here in y, we have not used every element of that set. In particular, if you look at, this number 1, that has not been used in our function relationship. And that's okay. There's nothing in the definition of a function that says that all of the elements of the codomain need to be actual outputs of the function. Okay, so now let's try to do something else here. Let's suppose that the arrow that joins 1 to 2, that is this arrow right here, let's suppose we were to erase that arrow and replace it with an arrow that sent 1 to 3. So we're going to imagine that this arrow is gone. Right here, that's gone. And now the only elements of y that we're using are 3 and 4. is this new diagram a function? I submit to you that it is a function because we are still using every element of x, and each element of x is being assigned to a single element of y. Now, the fact that one of these outputs, namely 3, is duplicated doesn't violate the definition of a function. So on this slide, we have several more examples of functions. So the first one is a function f from the real numbers to itself, where the formula is given by this quadratic polynomial. So let's just convince ourselves that this really is a function. So first, the domain is the set of real numbers, which means that we must be able to use every single real number in this function. And indeed, it's perfectly fine. Any real number can go in place of x. We can square it, we can subtract 3 times that number, and then add 2 to get another number. Right? So every single number can be used, and it does yield a single output, namely this x squared minus 3x plus 2. So in this instance, the real numbers is the set of all possible outputs. That is not, in this instance, the set of actual outputs, and you can see that by drawing a graph. Right? So if you graph this function, it is parabolic and looks something maybe like that. So these are inputs, these are outputs, and it bottoms out at minus 1/4. So if you take any real number less than minus 1/4, it will not be an output of the function. All right, so that's our first example. Second example doesn't really involve numbers at all. It involves words. So we're going to let W be the set of words in the book, and L is just our ordinary alphabet. We can define a function from W to L that takes any word as an input and as an output gives the first letter in that word. So for instance, if you wanted to take F of the word book, book is the input, and then B would be the output because that's the first letter in book. All right, now finally, in the third bullet, we have a little more complicated example. So here, F is a set of sets. In particular, it's a set of all non-empty finite sets of integers. And we're going to define a function S from F into the integers, where S is going to have as an input one of these finite sets of integers, and the output is just going to be the sum of all the entries. So for instance, if X is the set 1, 2, 3, consisting of 1, 2, 3, then the output is just going to be the sum of all of those numbers. So another example would be if we took S of, I don't know, let's pick our favorite non-empty finite set of integers. How about minus 1, 0, 1, 3? Well, we would just go ahead and add all those numbers together, and in this instance, we just get 3 as an output. Some functions have special properties that are of interest to us. One of those properties is injectivity. So we say that a function is injective, or one-to-one, if whenever we have two outputs, f of A and f of B, that are equal, then that implies the original inputs must have been equal to begin with. Now, an equivalent way to phrase that is by saying that if the inputs are different, then the outputs must also be different. So you might recognize that this statement here is a logically equivalent contrapositive version of this statement. Okay, now the figure that you see on the slide illustrates a one-to-one function. And how might we see that? Well, we should just observe that if you take any two different elements in the domain, they give rise to two different elements over two different outputs in the codomain. Here we show how to prove a function is one-to-one. So we start on this slide with a function f from the integers to the integers, given by this rule. And maybe we should convince ourselves that this really is a function. Indeed, if we take any given integer, we can multiply that integer by 2 and add 1 to get an output, a single output here that is again an integer. Now, we're not going to get all integers as outputs here. In fact, we can see that the only outputs we're going to get are odd integers. Now, we want to show that this function is one-to-one. To do this, we begin by supposing we have elements in the integers that give rise to equal outputs. That is, f of a and f of b are equal. To show the function is one-to-one, we need to show that the original inputs were equal. So how do we do that in this particular setting? Well, f of a is 2a plus 1. F of b is 2b plus 1. And now we can use some arithmetic to conclude that a equals b. So we first do additive cancellation on the ones, and then we can divide both sides by 2 to get that a equals b. So every one-to-one proof will look something like this, right? You start with outputs that are equal, you do some stuff, and then you conclude that the original inputs were equal. Another property of functions that's of interest to us is surjectivity. So we say that a function is surjective or onto if for every element in the codomain there exists an element x back in the domain where f of x is equal to y. So what this means is that all of the elements in the codomain y, rather than being just potentially outputs, are actually outputs, right? So that means everything in y is an actual output of the function. And the diagram that you see here illustrates that. So you go and look in y, and if you just pick anything at random within y, say this object, then there is an element back here in x that maps to that element, little y, under this function. Here we prove that a certain function is onto. So this function is one that you might not have seen before. It's called the floor function. And what it does is it takes a real number and sends it to an integer according to the following rule. So we take our real number, whatever real number we choose, like let's suppose it's pi, perfectly legit real number. And then what you do is you find the largest integer that is less than or equal to that input number. So pi is about 3.14, and so the largest integer that's less than or equal to pi would be 3. So let's do a few more. What about f of 3 itself? So the largest integer that is less than or equal to 3 is 3 itself. Okay, so that's the idea of this function. So we're going to prove that this function is an onto function from R onto the integer z. Now this proof, this onto proof, this proof looks like almost every onto proof on the earth. So how do you do it? Well, the first thing is you need to pick just an arbitrary element over in the codomain, right? So we do that. We pick an arbitrary element in the codomain, and we want to show it's an actual output of the function. That is, we need to find something back here in the real numbers that gets sent to that element of the codomain. So since the integers are in fact real numbers, we know that this element actually is a real number. And when we apply our function to that real number, just like what happened up here, there's no effect, right? If the input is an integer, then the output will be that same number. Therefore, we have found something back in the real numbers where f of that number is the output that we seek. All right, now again, every onto proof looks something like this. You start with something in the codomain, and then you go and you find something in the domain where f of that something equals the element of the codomain that you started with. So not every function on Earth is one-to-one and onto. So what do you do when you're presented with a function that's not one-to-one or not onto? How do you verify that? So we're going to see how you might go about that in this particular example. So we have our set capital E of even integers and our set capital O of odd integers. We're going to define a function from the Cartesian product E cross O into the integers given by f of x comma y equals x plus y. So now remember, E cross O, what is that? That's all ordered pairs where the first object is an even integer and the second object is an odd integer. So what's happening here? We're taking an ordered pair where the first object is even, the second object is odd, and then we're adding them together. So the question is, so this is a function, and the question is it one-to-one, and is it onto? So we want to prove or disprove this. Okay, so here's our solution to the problem that was given on the previous slide. So I want to remind you before we begin that this function, remember, it goes from the Cartesian product E cross O into the set of integers. And what does it do? It takes a pair, x comma y, as an input, and the output is x plus y. Now you might have been thinking already that if I take an even integer and add it to an odd integer, the result will be odd. And so that means that really all of the outputs for this function should be odd integers. And that means that not every element of the codomain is an output, right? Because the integers can have even integers as well. So we're going to first show that f is not onto. That is, not all of the codomain is used. So if f were onto, then 2, which is in the codomain, would necessarily be an output of this function. And so there would have to be an ordered pair back here in the domain where f of x comma y would be equal to 2. But that would say x plus y is equal to 2. But remember, x is even and y is odd. And so the sum x plus y must be odd according to one of the exercises that we've already done. And that's impossible because 2 is an even number, right? X plus y is odd, 2 is even, and there are no numbers that are both even and odd. Okay, the next thing we're going to do is show that f is not 1-to-1. And all we have to do there is notice that there are two ordered pairs, distinct ordered pairs, back in the domain that give rise to the same output, right? If you take 4 plus minus 3, that's the same as 6 plus minus 5, namely it's 1. So we have two equal outputs, but the inputs are not equal, and therefore this function is not 1-to-1. One special way that we can take existing functions and make new functions is through the use of what's called function composition. So let's suppose we have a function f that takes elements of x to elements of y, and then we take over with another function g that takes elements of y into elements of z. Then this new function g circle f is a function that takes x into z, and it does what you would expect it to do. So g circle f of x, to get that, you first apply f to x, and then you apply g to that result to get an element over in z. So first, you start with little x over here, you hop over to y with f of x, and then g takes f of x over to g of f of x here in z. Okay, so we have an example on this slide. So we let f be the function from r to r defined by this floor function that we talked about a little bit earlier, right? So f of x will take x, you look for the greatest integer that is less than or equal to x, and that's the output. And then g is just going to be the function from r to r that takes an input and multiplies it by 3. So let's compute both g circle f and f circle g. So both of these constructs make sense in this setting. So if we take g circle f, that would be g of f. Now f takes the floor of 2.4. So that's going to be the largest integer less than or equal to 2.4. So that would be 2. So then we take g of 2, which essentially tells us to multiply by 3, and we get 6. Now on the other hand, if we take f circle g, then that's f of g of 2.4, which would be f of 7.2, because remember, g takes things and multiplies by 3, and then f is the flooring function, so it's the biggest integer that's less than or equal to 7.2, and that would be 7. Now, one thing I want you to notice about this computation is that the order matters, whether we do g circle f or f circle g. That is the order in which the g and the f occur apparently is important because the outputs are different, right? G circle f is different from f circle g. So those are not equal to one another. So we finished the video with a couple of proofs involving function composition. So here we have two functions, f and a g, both of which are 1-to-1, and we want to show that the corresponding composition, g circle f, is also 1-to-1. So how do we show that a function is one-to-one? So let's suppose that we have two equal outputs. That is, suppose G circle F of some input A is equal to G circle F of another input B. We want to show that A and B were equal to begin with. So what does this mean? This means that G of F of A is equal to G of F of B. And so F of A must be equal to F of B because we know that G is a one-to-one function, right? So G takes F of A and F of B to the same output. And so the inputs, F of A and F of B, must have been equal to begin with. So this is because G is one-to-one. So now we just do more of the same. Therefore, A equals B. Because F is one-to-one. Right? Again, we have two equal outputs. F is a one-to-one function, and so the inputs A and B must have been equal to begin with. And so we can conclude that G circle F is one-to-one. Right, how do we know that? Again, remember, to show that a function is one-to-one, you take two equal outputs, and you show that the inputs were equal to begin with. Here we have another problem involving function composition, but this time, instead of looking at one-to-one functions, we're going to be looking at onto functions. So here we have a function f from x to y and g from y to z, and we're going to suppose that G circle F, the composition, is onto. And we're going to want to show then that the function G must be onto. So remember that G circle F, its domain is capital X and its codomain is capital Z. Okay, so how do we get started on this proof? So we want to show that G is onto. So that means we need to pick an arbitrary element in the codomain of G and show that it is the output of something in the domain of G. So here's an arbitrary element of the codomain of G. So we're going to let Z be in capital C. So we need to make use of the fact that G circle F is onto. So let's do that right now. So because G circle F is onto, there is an X back in the domain of G circle F, which is capital X, with G circle F of little x equaling little z. So let's see what that really means. So this means that g of f of x is equal to z. But now I want you to look at this element f of x. Right? This element f of x, that's an element of y, right? So f of x lives here in y. Right? So, but f of x is an element of y. So there is a y in capital Y with g of y equaling z. And from that, you can conclude that g is onto. Okay, something a little bit interesting about this example is that you can have this situation in place, right, where g circle f is onto. That means that g must be onto. But it turns out that f does not need to be onto. And to see that, let's suppose we have sets x, y, and z, where x consists of two objects, y consists of two objects, and z consists of a single object. And we have functions defined as follows. So let's let f behave this way, and we'll let g behave this way. Then we can see that, right, so f goes from x to y, and g goes from y to z. We can see here that g circle f is onto, right? If you take anything in z, it comes from something back here in x. In fact, they're both objects in x get sent to that element in z, but the function little f is not onto.